This video will go over how to calculate the concentration of an unknown solution in a redox titration. In this titration, 0.0500 moles per liter of acidified iron 2 sulfate was titrated with an unknown concentration of potassium permanganate. And we're going to figure out the concentration of this permanganate. Below is 4 titrations summarized. The first thing I'm going to do is go through these titrations and analyze those. We want to keep any titrations that are within or plus or minus of each other of 0.2 milliliters. If a titration is further than 0.2 milliliters away, for chemistry 30 you should exclude it. So the very first titration, if we look at the volume used, if you take the final minus the initial, the first titration used 12.75 milliliters and the student recorded a dark purple color. Okay, most likely added too much permanganate. In the second titration, when you take the final concentration minus the first, you get 12.51 milliliters. Lower than the first trial. In the second trial, the final concentration minus the first was 12.49 milliliters. Quite close to our second trial. In the last trial, the faintest purple was achieved, but the volume was 12.10 milliliters. Often students put a lot of emphasis on these faint colors, but you have to remember there's a lot of steps in titrations. You had to pipette, you had to measure your initial and final volumes correctly, and in this trial, the last one, it is more than our 0.2 mils low. So we are not going to include this last titration in our average and the first one that had the dark purple and the high volume, because it's more than 0.2 milliliters from the next closest. So our volume average of permanganate we're going to add up our good trials and divide by the total. So we have 12.51 milliliters plus 12.49 milliliters. There are 2 trials in total, so we'll divide that by 2, and we get an average of 12.5 milliliters. So now I have all the information I'm going to need except for the balanced equation. We know the original concentration of our iron sulfate. The potassium permanganate is the one thing we need to find out. The one other thing we'd need to know that was not previously written down is that the A10.00 milliliter pipette was used with the acidified iron 2 sulfate solution. So I'm not going to go through in this video how to balance the equation. You would have to make a list of all the species present, find the strongest OA, find the strongest RA, and net it up. The strongest oxidizing agent is the permanganate with acid, and the iron 2+ was the strongest reducing agent. And when you balance the electron exchange, you end up with 1 permanganate aqueous and 8 H+ ions and 5 iron 2+ ions. And that's going to create 1 manganese 2+ ion, 4 water, and 5 iron 3+. We no longer see the 5 electrons that were transferred from the oxidizing agent to the reducing agent. I like to make a little bit of a summary below my reactants just to keep everything straight. So the permanganate is what we're trying to find out. I'll end up calling this the unknown. The volume, which because this is the titrant, was the average volume of the good trials, was 12.5 milliliters. The acid is an excess reagent. Whenever there's 3 chemicals, 3 reactants, one of them will be in excess. Okay? The other 2 will run out at the exact same time with only an equivalent amount of each. The iron, a 10 milliliter pipette, was used. It just wasn't typed out. I just mentioned it orally about a minute ago, and the concentration is given in the question. I'm going to go through the 3 steps you can always use for Chem 20 or Chem 30 titrations. The fact this is a redox titration doesn't change the sequencing. This is going to be our known in terms of moles, because we know the C and the V. In terms of moles, this is going to be our unknown. And you always have to start with the chemical that you can get the known amount of moles with at the beginning. So the 3 steps I always go through are, first, we want to get the moles of the known. That'll be our iron in this case. Second, you're always going to convert the moles of the known to unknown. So moles of the known. I'm just using N for moles. For this step, we're going to need that balanced chemical equation. Then finally, we can get the concentration of the unknown, because we'll know it's C. We'll know the moles and we'll know the volume. So we'll start with getting the moles of the known. Concentration equals, and for titrations, most of the time you're going to be doing C times V to get your moles. Concentration is given and nicely summarized below this chemical above. Times, you got to watch our units. We don't have liters here. So to turn milliliters into liters, we have to divide by 1,000. So I'm not showing that. I've converted that 10.00 mils to liters. And that's the moles of iron. Liters cancel. Next, our stoichiometry step, or stoic step. We're going to convert the moles of iron that we just figured out into how many moles of permanganate there must have been at the equivalence point when we got that faint purple. This is moles, and I like to write in the chemical, that's Fe2+. I'll just leave out the fact that it's aqueous. And now our conversion, we want to get rid of iron 2+ moles. So I'm going to put its stoichiometric ratio on the bottom, and we want to figure out permanganate's moles. So we'll need that stoichiometric coefficient on the top. So we have 5 iron moles are going to react with 1 permanganate. So let's see, the permanganate is a 1 and the iron is a 5. So the moles of permanganate that there must have been at the endpoint, 0.001000 moles. Almost done. Last, we want our concentration of unknown, which was our permanganate. And now we have the pieces. We know the N above and we know the volume. So our moles of permanganate on average at the endpoint divide by the average volume is our 12.5 for those two good trials. Okay? We do want to have moles per liter, so I'm going to convert that 12.5 milliliters to liters. We end up with 0.00800 moles per liter. So that is how you calculate the unknown concentration in any titration, and specifically in this example for a redox titration.